By now you're probably really flooded with all this information. Hilbert space, Dirac notation, the brackets, probabilities. Well, I'm afraid we're not quite ready to discuss one thing that was on our minds from the very beginning, and that is, what's the difference between unpaired and paired electrons? If you remember in that very first one, I said I'm going to pick on those atoms with an unpaired electron, like copper, silver, gold. Well, we've got just a few more pieces to get to before we can totally explain that. And one of those things is the idea of an operator. An operator shows us what the observables are going to be. Now, remember, we already know what the observable is on these things. That's usually plus or minus h bar over 2, which have been shown by experiment. So this is not going to show us anything new that way, but it is going to show us how measurement bases affect one another. But that's way down the line after we get to the infinite dimensional Hilbert space. Now, this kind of abstraction probably tells you why there's not a lot of people in quantum mechanics and why there's not a lot of quantum chemists around, because they get to this point and they say, well, let's go back to the lab and do some reactions. I can't handle this low-level stuff that tries to explain why all these chemical properties occur. So let's dive into spin operators, and if you're still with me, you can follow along. As usual, I've filled the board with stuff and made just enough room for my face here. I've shown each of these items, which we should be familiar with from the other videos. This represents simply the plus z. This represents simply minus z. And this represents 1 over square root of 2 times plus z plus minus z. And this represents 1 over the square root of 2 plus z minus a minus z. And for good old y, where we have to get involved with imaginary, it's 1 over the square root of 2 plus z plus iz, and 1 over square root of 2 plus z minus iz. If you're way lost with this, you really need to go back and look at the probabilities for Z, X, and Y videos, because this is just going to be total garbage otherwise. Now, earlier we found out that the measured value was h bar over 2, and this was measured in the lab. So what's this? What's this all about? What we're showing is if we put this spin operator in the z-axis to one of these vectors, we get the measured value back and that same vector. Now this is really important in the fact that this relationship is called a eigenstate, and this is the eigenvalue. And you're just going to have to follow along, because I can't really make it more clear than just grinding out the results here. This is a 2x2 matrix, and this 2x2 matrix will preserve this relationship here. And what I've done is actually cranked it out for myself to prove to myself that that's the case. This item here, the 2x2 matrix and the h bar over 2, those are used in each of the scenarios. This is the plus Z scenario, minus Z scenario, plus X minus X, plus Y minus Y. Let me walk through this. If your linear algebra is no good, then let me help you out with this. We're starting with this first one in its matrix representation. H bar over 2, 1, 0, 0 minus 1. This is the spin Z operator right here. This is spin Z operator. This is spin Y operator, spin Y operator, and spin X operator, X operator. So we've got each one of these is multiplied times a column vector. Here's the plus Z column, plus Y vector. See that 1 over square root of 2 comes out there. And the minus Y plus X minus X vector. So what we want to see is the relationship like this, where we have the vector, the H bar over 2 comes out here, and the vector itself. So here's the eigenvalue, here's the eigenvector, or the eigenstate. To come up with this value right here, I have to combine the row and the column together. 1 times 1, 1, 0 times 0. So here's the 1 when I calculated this first element, which is the row and row 1 column. And this is the second element, row 2 column. Here's row 2, 0 times 1 is 0, negative 1 times 0 is 0. So that all works out. Some of these others are not so easy, but let's just keep going and see if we can make it. To calculate this element, we take this row times this column. Now see if you can kind of think through that without me jabbering about it each time. That gives us a 0. Now prove to yourself that we get a negative 1 here. 0, 0, minus 1, minus 1, minus 1. Now you'd say, oh, you didn't get the same vector back. Should have got a 0, 1 back. Oh, well, you can factor out a negative 1 because the eigenvalue is not plus h bar over 2, but minus h bar over 2. Now we get down into the y, and things get a little messier because we got this 1 over square root of 2 in the way, but that's just a constant, so that can be pulled out in front, like you see here. So let's work through this. To calculate this element, you take this row times this column. You get a 0 plus I squared minus, which is a plus 1. Plus 1. How did we do that? You might want to walk yourself through that again a little bit. And let's see, what do we do? This is row, for this element, we do row 2 times this column. So that's going to be I plus 0, which is I. No headache there. Maybe it'd be best if you freeze frame it and walk through each one of these and prove to yourself that it works out. I'll do one more because it gets pretty old walking through all these little things. To calculate this element, we multiply row 1 times column 1, and if you multiply that out, you get a negative 1. Row 2 times column 1 gives you a 1. Well, it just gives you a 1. And then we factor out the negative value, and then we got the same vector back. Okay, oh man, that was detailed. So maybe when I do these matrix things again, I'll just have you kind of walk through it. You probably totally forgot about what this topic is. What is this, quantum chemistry? What are we doing, talking about electrons? That's what we're supposed to be doing, and we actually are. But have to prove some stuff. Now, a lot of books just gloss over this without forcing you to walk through it, but I need to believe it before I start spitting this out on a video. So that's all for this video, but we're going to have more on spin operators coming up next.